Let's take a look then at how to represent the equation of a plane. Okay, we're going to start by looking at the vector equation of a plane. Now if you think about it, a plane it's a flat two-dimensional surface that lies within the three dimensions. And if we're thinking about using vectors to describe this surface, like we need some way of getting everywhere along this plane that we want. So we can start with the vector A. Okay, so I can say R would equal A. So that initial vector takes me to a point on the plane. But while we're there, we need to be able to move anywhere that we want along the plane. So if I include a multiple of a vector B, if B is a vector that lies within the plane, then that's going to allow me to move along some of the points that lie within the plane. But not all of them. Okay? Like essentially what we're doing there is we're describing the equation of a line, aren't we? Like we're familiar with this already. Like this represents the equation of a line. It takes you to a point on the line and then you move along the line. But because we're trying to describe a surface that doesn't just have one vector that lies within it, we need more than this. Okay? And what we could also include is another vector C. And providing that these two vectors that we're using, that they both lie within the plane, that allows us to move anywhere we want along this surface. Because just by varying what lambda and mu are, say if lambda was 1, we'd move one lot that way. If mu was 1, we'd move one lot that way. And that would take me to that point on that plane there, wouldn't it? But if I wanted to move to another point, say over here, we could let lambda equal 2 and it'd move us further this way, and then mu would equal 1. So just by using two vectors that lie within the plane, as long as those two vectors are not parallel, like if both vectors were parallel, if we combine multiples of those together, it would limit us to just moving along that direction, wouldn't it? So we wouldn't be able to actually move in all of the plane. They don't need to be perpendicular to each other. They could just be like any two vectors that are not parallel. So we could have a vector like this and a vector like this, and as long as they both lie within the plane, we can combine multiples of those to go wherever we want along that plane. And obviously if you wanted to go this way, we could let lambda equal -1 and it'd take us that way, and we could get to say a point over there. If lambda was -1 and mu was 1, we could get there, couldn't we? So that it's good if we can understand where it comes from, but like essentially we just need to know, like from the exam, that this form here is the first type of equation of a plane that we can look at using vectors. Okay, where A represents a point which lies on the plane, and those two represents vectors in the plane. Not parallel. Okay, just two non-parallel vectors that lie within that plane. Alright, so let's try example 1. Okay, so example 1, it says find the vector equation of a plane that contains these 3 points. Okay, so if you think about visualizing this, we've got a plane, and within that plane, 3 points are contained. Okay, so if we're thinking about using this form, we can use any of these points. Like if we're starting at the origin, like A, this written as a vector would take us to the plane, B would also take us to the plane, and C would also take us to the plane. But I suppose by convention we should use the first coordinate that we know, although we could use any. Okay, so we know 3 points in the plane. We now need to figure out two vectors that lie within the plane, because if we can find two vectors that lie in the plane, multiples of those allow us to move around in the plane, don't we? Okay, so I'm going to use the vector from A to C and the vector from A to B, because those two vectors would allow us to move around. Okay, so all we need to do then is find the vector from A to B. which is b minus a, or think about this from a to b, it'd be 1 minus 3, 7. And the vector from a to c would be 3 minus 1, 8. So now we've got enough information, we can write the plane. Point 2, 1 minus 3, and then multiple of these two direction vectors. It is worth checking that those two directions are not parallel with each other, but clearly that vector is not parallel with that vector, so that because they're not parallel, it allows us to move wherever we want within that plane. Okay. Example 2 says find the vector equation of the plane which contains this line and this point. So try and visualize what's going on. There's a plane, and within that plane there's a line contained. Now this line here, we know, passes through the point 1, 5 minus 2, and the line is moving in the direction 3 minus 4, 1. Okay. So we also need a bit more information. If we're trying to describe the plane itself, we need to know a point, and we need to know two vectors that lie within the plane. At the moment we've got 1 point, and we've got one vector that lies in the plane, or one direction. But what we also know is there's another point, 4, 5 minus 3, which lies somewhere else within that plane. Okay, so we can use that information to figure out another vector that lies in the plane. Okay, if I wanted to figure out another vector that lies in the plane, the easiest way for me to do that would be to get the vector between the point 1, 5 minus 2 and the point A. Okay, so I should literally label that point, let's call that one the point B. So from B to A, if I was going to go from there to there, the direction would be 3, 0, minus 1. Okay, so from B to A, it would be A minus B, which would give us 3, 0, minus 1. Okay, now we've got enough information. We've got two vectors that lie in the plane. We've got a point that lies in the plane. So we could say that the plane would equal 1, 5 minus 2 plus lambda 3 minus 4, 1 plus mu 3, 0 minus 1. Okay. The next type of equation of a plane we're going to look at uses a dot product. Okay, let me just clear this up and we'll have a look at that. Okay, so if we're going to use the dot product or the scalar product, this can give us another way to think about the equation of a plane. One thing that we've not mentioned yet that I probably should mention, right? When we're trying to represent the equation of a plane, which is like a well, it lies within 3 dimensions, but it's like a flat surface, isn't it? So you guys can see that. Imagine it's like infinitely thin. Like if I was trying to represent this equation for this plane, the weird thing about it is there's actually like an infinite number of different vectors that lie within the plane. So like, yeah, we can use 2 of them. Like if we know 2 of them that aren't parallel, we can combine those 2 together and we can move around the plane. But there is one unique direction that actually perfectly, instead of worrying about like all the different possible vectors that lie in the plane, there's one vector that we can use which perfectly describes the direction of this plane. Like if I know the vector that is perpendicular to the plane, can you see that there's only, no matter whereabouts this plane is or whereabouts I am on this plane, the direction that's perpendicular to it is always pointing in the same direction. So most of the exam style questions that we'll actually focus on, if you're thinking about the direction that the plane is going in, the most useful thing to use is actually the normal vector to the plane, because that normal vector is just one vector that we can use, and it perfectly tells us the orientation of the plane. It doesn't lie within the plane, but it's one vector that allows us to describe the direction that the plane's going. Okay, so if you look at this diagram here, if we knew what vector was perpendicular to the plane, let's call it the normal vector, then this is going to give us a way of describing the plane. And we don't need to know two vectors that lie in it, we just need to know the direction that's perpendicular to the plane. Okay, obviously if we knew two vectors that lay within the plane, like A and B, and I wanted to figure out what this normal vector was, can you see that if we cross product those two vectors, that would give us the normal vector, wouldn't it? Because don't forget, when you cross product two vectors, you end up with, I've actually drawn that the wrong way around, that one should be B, and that one should be A. If we apply the right hand rule, A, B, N. So if I cross product, if I need two vectors that lay in the plane, if I cross product them, I'd get my normal vector here. But I mean, sometimes in the question, it might just tell us the normal vector. So if we already know what the normal vector is, there's a quick way of us thinking about the equation of the plane. Okay, so think about this again. We've seen this notation before. Like A is a vector that takes us to the plane. R is just a general point somewhere on that plane. That vector there would be R minus A. Like if we go minus A and R, the vector R minus A is a vector that lies within the plane. Okay, so what we've got here, we've got a vector that lies within the plane, and we've got a vector that's perpendicular to the plane. So can you see that clearly? If that vector lies within the plane, the normal vector has got to be perpendicular to that vector, hasn't it? Like just if we go back to this, and if I think about my normal vector here, any vector that I draw within this plane, if I do the normal vector, apologies you can't see that very well, if I do the normal vector, it'd hit that vector at a right angle, wouldn't it? The normal vector would hit that vector at a right angle as well. Okay, so we know that if this is a vector within the plane, we know the normal vector is going to be perpendicular. So we could say therefore R minus A dot producted with the normal vector must equal 0. Because that's a property that we knew about from last year, isn't it? Like if the two vectors are perpendicular, when you dot product them, the answer is 0. Okay, so that gives us another version. You might see this written as R dot N equals A dot N. And if you do see it written in this form, don't forget when we do a dot product of two vectors, like these are two vectors that we'd know, like A would just be a point in the plane or a vector to the plane, and N would just be a perpendicular. So what we end up with on the right hand side here, when you do the dot product of the two numerical vectors, you end up with a constant. It's not a vector. Okay, I think on the sheet I've used the letter P. Well, you can use any letter that you want, but you've got to realise that like if you see the equation of a plane written in this form, that there represents the normal vector to the plane, and that there will just be a constant. But what it really represents is the dot product of the points and the normal vector. Alright. Okay, so let's try one example. I'm just conscious the video is getting quite long. Let's try one example. Okay, so example 2 says, find the equation of the plane which is perpendicular to this vector, 2 minus 3, 5, and the plane contains the point 3 minus 2, 4. Okay, so if we visualize this, the direction of the plane we don't know, but what we do know is the plane is perpendicular to the vector 2 minus 3, 5. And we know there's a point that lies within the plane, which is A, which is 3 minus 2, 4. Okay. So I can say, well, therefore, R minus A, which is 3 minus 2, 4. You know, that would give me this vector here. And if I dot product that with the normal vector, which is 2 minus 3, 5, the answer would be 0. In other words, R dot 2 minus 3, 5 would equal 3 minus 2, 4, dot product with 2 minus 3, 5. Don't forget, when we do the dot product, we literally just multiply and add. So that would be 6 plus 6 plus 20. Okay, so we'd get R dot this would equal 32. Alright. There is one other equation of a plane that we need to look at, which is the Cartesian equation. We've actually already seen it in the Cartesian form when we were thinking about intersection of planes and we were using matrices. But now we can actually think about why that equation looks like a plane. Okay, nice one, guys.